Hello everyone, welcome to the uh, second video of torsion. In this video, we will be discussing about the tor derivation of torsion equation. So in this case, again, a cylinder is subjected to twisting moment, and here this end is supposed to be fixed. This end is supposed to be fixed, similar to the diagram shown in the introduction video. This end is supposed to be fixed, and the other end is supposed to be free. View. And the side view is also shown here. Side view is also shown here. And in the side view, a thin strip is imagined. This thin strip is imagined at a radius of r, small r from the center, and with a thickness dr. So the thickness of the strip or the annular section is dr, very small thickness. We are assuming a very small thickness of dr, elemental thickness of dr, at a radial distance of r, small r from the center. Now, this end is fixed. And you can see the line AC here. You can see the line AC here. Initially, the line is a horizontal line, AC. And when the twisting moment is applied here, when the twisting moment is applied here, like this, when the twisting moment is applied like this, when the twisting moment is applied like this, you can see that the position of C remains as such. There is no change in the position of C because this end is fixed. This is a fixed end. But the position of A changes to B. That is, line AC is rotating with center C to the new position BC. Now, I would like you to remember the definition of shear strain. Now, shear strain was defined as the change in angle between two lines which were initially perpendicular. The change in angle between two lines which were initially perpendicular. Here, the two lines which were initially perpendicular are AC and this line indicating the fixed end. These were initially perpendicular. And after the twisting moment was applied, now there is a slight rotation. The AC has changed its orientation. Now the change in angle is phi. So we can say that phi is nothing but the shear strain due to the applied twisting moment. So phi is the shear strain due to the twisting moment. With this in mind, we can proceed to the derivation. So phi is the shear strain. It is written in the text here. The shear strain phi of the elements at a radial distance r from the axis is constant for a particular value of t. This remains constant whenever for a particular twisting moment, the shear strain remains a constant at any radial distance r. Now here there is something I missed to explain. That is, this line and this figure, the elevation figure, it is not of the entire cylinder. The portions beyond the thin strip of the annular strip is trimmed off. We are not considering that here. This line AC is drawn over the extrusion of this thin strip behind. Okay. So what we are saying, this A and A coincide here. There should be material over this, like this. There should have been material over this. There should have been material over this, but for the sake of simplicity of the figure, uh, that part is trimmed off. So that is not necessary. Not necessary. We need to consider only the thin strip in our derivation. Now, so I want to stress upon what we discussed in this video so far. That is, uh, for a particular twisting moment T and a particular radial distance small r, the shear strain will always remain a constant. Now let us move on to the next. Now we are considering arc B. Okay, we are considering the nature of arc B. From the geometry of the figure, we can say something about arc P. See, from this figure, we can say that this side view, this figure, we can say that arc B is, whenever we need to calculate the distance of an arc or the length of an arc, that is a radius into theta, radius into angle. So here I can say that from this it becomes small r into theta, small r into theta. From this here again, the same AB, the same point we are tracing here, A and B, same length should have to be obtained from this figure also. And from this figure, the radial distance is nothing but AC, which is nothing but the length of the shaft. So it is L, L into here the angle by which AC rotates is phi. So L phi can be considered as L phi. So the arc length AB, from this figure it is r theta, and from this figure it is L phi. So that is what is written here. Arc B is nothing but r theta and L phi. Now we have already established that phi is nothing but the shear strain. Phi is the shear strain. So shear strain stress, as a corollary of the Hooke's law, we can apply that to the shear stress and shear strain also. Then we can write that shear stress is equal to G into the rigidity modulus into the shear strain. So tau should be proportional to phi, and the proportionality constant is nothing but G. So I can write phi is nothing but tau by G. The shear stress is, sorry, shear strain is stress by modulus, rigidity modulus. So I have replaced phi by tau by G. Then rearranging, we have taken r theta part, r theta and tau by G. Now when we are rearranging it, this L into tau by G, then rearranging that we can write as tau by R is equal to G theta by L, where tau is the shear stress, R is the radial distance of any point we are considering, G is the rigidity modulus, theta is the angle of rotation of a cross section, and L is the length from the fixed length. So that is the first part of the derivation, first part of the torsion derivation. Now we have some more part. We need to look into the force balance. So what is the tangential force on the thin section we have considered? We have considered a thin annular section. So what is the tangential force? Force is nothing but stress into area. Stress into area. Now it is a small area. Going back to the figure, it is a small annular ring. So that is, the area can be considered as circumference into thickness. That is 2 pi r into dr. So we are considering the area of this annular ring as 2 pi r into dr. So area into stress gives us the force. So that is what is written here. Tau into 2 pi r dr. Shear stress into area gives us the shear force or the tangential force. Now the moment of tangential force on the element. What is the moment caused by this force? Moment is nothing but force into a radius. So I am multiplying again this with a radius r, small r. So tau into 2 pi r dr into r. So that is the moment caused by the moment developed due to the shear stress, the resisting moment offered by the cross section. The sum of moments of the whole shaft. So this, now we have considered this small strip only at the radial distance r. Now the entire moment offered by the resisting moment offered by this cross section. How is the resisting force developed at every point? Resisting stress is defined as the resistance offered by the body. So what is the total resistance offered by? What is the total resistance offered by the entirety of the cross section? Then we can see that is we have to integrate 0 to r. Okay, we have to integrate. We are not doing the integration process here, so we are not marking the limits here, but we have to integrate it from 0 to r, capital R, that is the total radius of the cross section, into the moment, the equation we have established above. Now again, in this case, tau is being replaced again. From the first part of the equation, I can write tau is nothing but g theta into small r by L. G theta into small r by L. So that is again written at the bottom. I have replaced tau with uh, this form of the equation. Again, g theta by L remains a constant. G theta and L remains a constant. Now R is a variable, so R is to be written inside. So this becomes integral 2 pi r dr into r square. Now integral 2 pi r dr into r square for any circular cross section. For circular cross section, if this is the in my drawing, if this is the center. For an axis passing through the center, axis passing through the center. So this is supposed to be a circular cross section. This is an axis passing through the center. This axis is perpendicular to this circular cross section. So for any such system, this is the equation, defining equation for polar moment of inertia. This is the polar axis. This longitudinal axis. For a rod or bar, we call it the longitudinal axis. But for a cross section, it is the polar axis. It is the polar axis. So about this axis, the moment of inertia of this cross section about this polar axis is given by this equation. You can refer back to your basic engineering mechanics textbook. This equation as such it is given in the textbook. So this directly we can write it as the polar moment of inertia. Polar moment of inertia. That is, in the mechanics test you would have studied it like this. That is, this is a circular cross section. This is IXS, IXX. This is the moment of inertia about this axis may be called as IXX. Moment of inertia about this axis may be called as IYY. Now I am talking about an axis going into the plane of the screen. That is this one. This is supposed to be ZZ. Now IXX you already know it to be pi d raised to 4 by 64. IYY is also same pi d raised to 4 by 64. Now you might have studied in perpendicular axis theorem that IZZ is nothing but IZZ is equal to IXX plus, and not repeating the x and y. It is understood. IXX and IYY. IXX and IYY. This is the perpendicular axis theorem. So pi d raised to 4 by 64 plus pi d raised to 4 by 64 will give you pi d raised to 4 by 32. Okay, pi d raised to 4 by, for a circular cross section, the IZZ value is pi d raised to 4 by 32. Pi d raised to 4 by 32. Pi d raised to 4 by 32. So this IZ in the mechanics textbook, you might have studied it like this IZ. But here we call it as the polar axis, or the polar moment of inertia. So that is nothing but pi d raised to 4 by 32 for a circular cross section. When the shape of the cross section changes, if it is not circular or if it is a hollow circular cross section, then it changes. So that we will be discussing in the later classes. But as of now, we can understand that it is the polar moment of inertia, polar axis. So we can write it is represented, polar moment of inertia is represented instead of IZZ, it is represented here as capital J. This is the polar moment of inertia. Pi d raised to 4 by 32 for a solid circular cross section. So again we can rearrange it. T by G theta by L is equal to T by J. We can write it as such. Okay, T by J is equal to G theta by L. So G theta by L is tau by R, and from this equation, G theta by L is also equal to T by J. So the final form of torsion equation is this. It has three terms. T by J is equal to tau by R, which is also equal to G theta by L. Capital T is the resisting twisting moment offered by a cross section. A resisting twisting moment offered by a cross section. The resisting twisting moment should be equal to the applied twisting moment. So both are, some textbook write it as applied twisting moment, twisting TM, applied twisting moment. Some textbook write it as resisting twisting moment. The magnitude of both are equal, because when you are applying something, resistance should also be equal in nature. So T is actually the resisting twisting moment offered by a cross section. So T, the other terms I have already explained before, G theta and L. Now J is the polar moment of inertia. I have already established that it is IZZ. Now we need to further look into what is J, what is moment of inertia. Moment of inertia is something. Okay, the terms say that it is the resistance, it is inertia. So when I say moment of inertia, it denotes how difficult it is to rotate a cross section about an axis. So from this figure, from the earlier figure, when I am applying a twisting moment, like this, in the introductory class, we have already established that all the cross sections are rotating by some angle theta. So this rotation is taking place about the longitudinal axis. Now I am trying to find out by J, or polar moment of inertia, tells me how difficult it is to rotate, a cross section about the polar axis. How difficult it is to rotate the polar axis, rotate the cross section about the polar axis. So moment of inertia always gives us, it's the physical relevance of moment of inertia is that how difficult it is to rotate about some axis. If it is IXX, we are saying how difficult it is to rotate about XX axis. If it is IYY, we are talking about the difficulty of rotating it about the YY axis. Now, here we are talking about how difficult it is to rotate about ZZ axis, or the polar axis. So that is what J stands for. How difficult it is to rotate a cross section of a specific dimension about its polar axis. Thank you.